Today is 91-1, System of Equations, and we're taking a look at a system of nonlinear equations. And so we're going to solve a system of nonlinear equations. Now the graphs of the system of equations that are going to be nonlinear have either no point of intersection or one of more points of intersection. Now the coordinates of each point of intersection are going to be represented as a solution to the system of equations. And we're going to see imaginary numbers when they're nonlinear, and so when they are imaginary numbers, that means that they're solutions to the equations, but they're not going to represent a point of intersection. So let's look at a few problems. Our first example, we have x squared plus y squared equals 25, and then 3x minus 4y equals 0. So what we're going to want to do here is, if they're both like x squareds and then we have y squareds, we could use the elimination method to be able to do that. But because these are not considered like the same term, we're not going to be able to use elimination. We're going to want to use substitution. So with this 3x minus 4y equals 0, I want to solve for a variable. In this case, I want to get x by itself, so I'm going to add 4y to both sides. 3x equals 4y, divide both sides by 3, you're going to get x equals 4 over 3y. And so now I want to take that 4 over 3y and I want to substitute it back in for x into the other equation. And so substituting it in for x, you get 4/3 y squared. That square is going to go with the 4, the 3, and the y. So that's how I get 16 over 9y squared. And so I have to add these together. And to do that, do the common denominator. So pretend that as like a 9 over 9y squared. And so 16 plus 9 gives me that 25 over 9y squared. Then I want to divide both sides by 25 and multiply both sides by 9. And so the 25's cancel out, and so you're going to get y squared equals 9. And so now, square rooting both sides, you're going to get y equals plus or minus 3. So now these are my values for y, and I have to take both of the plus or minuses and I need to plug them back in to the original equation. So I have to take positive 3 and plug it in, and I have to take negative 3 and plug it back in. And so I'm going to use this equation right here that already has x represented, or x being by itself. So plugging in positive 3, the 3's cancel out and I get 4. Plugging in negative 3, the 3's cancel out and I get negative 4. And so my solution is going to be 4, positive 3, and negative 4, negative 3. And that's going to be my solution. This is what it's going to look like if I were to graph it. And so those were my solutions that I had just found, that point and that point right there. Example number 2. This is going to be a line and this is going to be a parabola. Now my y is already by itself, so I can just take it and I can substitute it into the equation. And so it's going to be, this piece right here is what's being substituted in. And so I get x plus 3 minus x squared equals 5. Now I just want to turn this into standard form. So I just rearranged it, put the minus x squared first, then the plus x, then the 3, and that equals 5. Then I could subtract 5 on both sides. And that's how I get the negative 2. And then divide everything by a negative. And so that's how I'm going to get the x squared minus x plus 2 equals 0. And so in this case, you can try and factor it. It's not going to factor, so we're going to have to use the quadratic equation. And so plugging everything into the quadratic equation, I'm going to get x equals 1/2 plus or minus the square root of 7 over 2i. And so now that I know what x is, I need to take that and I need to plug it back into my equation to either this one or this one to find what my y is. It's going to be easier to plug it into this top one here because then you don't have to deal with that square. And so this is me plugging in the positive version, because there's a plus version and then there's a minus version. So this is me plugging in the positive version in for x. So solving for y, I have to subtract the 1/2. That's going to give me 9/2 here. I have to subtract the square root of 7 over 2i on both sides. And so I'm going to get y equals 9/2 minus square root of 7 over 2i. Now I have to do the same thing with the negative, and so we'd pretend like it was a negative here. I would still subtract the 1/2, so I'd get the 9/2, but then instead I'm going to be adding the root 7 over 2i, and so it would end up being a positive root 7 over 2i. And so my solutions, when I plug in the positive, I get that one, right? So that's why here's my x value, here's my y value, and then when I plugged in the negative, that's how it switched, and so that's why it's a positive. And visually, this is what it looks like. Now, going back to this, if you notice my solutions, they're imaginary values. That represents they're not going to intersect. And so visually, if we're taking a look at this, there's no intersection here. And so it corresponds to what my solutions were. Example number 3 here. Now notice, because these are both x squareds and these are both y squareds, I could actually use the elimination method to be able to solve for it. And so with these system of equations here, if I multiply this side by 5, or this equation by 5, these are going to be opposites. This is going to be a positive 5, and this is going to end up being a negative 5. And so adding the equations together, they're going to cancel out here. And so I'm going to get 17x squared, and this is going to be 34. Divide both sides by 17, I get x squared equals 2. Take the square root of both sides, and so I'm going to get x equals plus or minus root 2. And so now I have to take that plus or minus root 2 and I have to plug it back in. And so I'm just going to plug it back into the bottom equation here, and I'm going to start with the positive root 2. And so square root of 2 squared, that just becomes a 2. 3 times 2 is 6. Minus 6 on both sides. That's how I get the negative 7. Divide everything by the negative 1 and I get y squared equals 7. Square root both sides, and I'm going to get y equals plus or minus the square root of 7. And so this means that when I plugged in my positive root 2, it's going to pair with both a positive root 7 and a negative root 7. So now I want to do the same thing with my negative root 2. And so plugging in the negative root 2 squared, once again, if you simplify it all, is going to give me plus or minus root 7. And so that means my negative root 2 is also paired with positive root 7 and negative root 7. And so my solution, I just have to write root 2 being paired with root 7, root 2 being paired with negative root 7, negative root 2 being paired with root 7, and negative root 2 being paired with negative root 7. And so there are my solutions. And so visually, this is where we're going to see it. This is about where negative root 2 is. This is where our positive root 2 is. And there's our positive root 7 and our negative root 7. Our last one here, example number 4. For down here, once again, because we don't have x squareds and y squareds to be able to do that with, we're going to have to use our substitution method. So with this x, y equals 3, if I divide both sides by x, the x's cancel out here, and that's how I get y equals 3 over x. So then I want to take this 3 over x and I want to plug it back in to the other equation because we're using the substitution method. That square is going to get paired with the 3. That square is going to get paired with the x. And so 3 times 9 gives me the 27. And now to get rid of everything out of the denominator, I have to multiply everything by x squared. And so that's going to give me x to the 4th minus 27 equals 6x squared. Subtract the 6x squared on both sides. Now I'm going to get x to the 4th minus 6x squared minus 27 equals 0. This is going to be one of those quadratic type equations, and so I can say u equals x squared and substitute u into my system of equations here. So I can substitute u into my equation here. And so then I get u squared minus 6u minus 27 equals 0. Now that's going to factor into u minus 9, u plus 3 equals 0. Set each one equal to 0, solve for u. Plug x squared back in for u because we're trying to solve for x, not u. If I take the square root of both sides, I'm going to get x equals plus or minus 3. and x equals plus or minus I root 3. And so now I need to take these values and I need to plug them back in. And so if I plug in 3, I get y equals 3 over 3, which is 1. If I plug in negative 3, I get y equals 3 over negative 3, which is negative 1. If I plug in I root 3, okay, if you have to rationalize this, because you have to multiply top and bottom by root 3i. And so what ends up happening is you get a negative 3 on the bottom, and that's how it's going to cancel out there, because if you rationalize it, and that's going to give me negative I root 3, you have to do the same thing here, and you're going to get I root 3. And so my solutions, when x is 3, y is 1. When x is negative 3, y is negative 1. When x is I root 3, y is negative I root 3. When x is negative I root 3, y is I root 3. And so here, I only have 2 points of intersection. This is not a representation of where it's going to intersect on my graph. And so taking a look at the graph, as you can see, those are my points of intersection. Now in conclusion, some of the things that we learned today were to solve a system of nonlinear equations. We took a look at equations in different forms. We had to use both the substitution and the elimination method to be able to solve them. And what I want you guys to go ahead and leave in the comments are, what do imaginary solutions represent graphically? And then in your own terms, what are some of the observable differences between the process of solving a system of nonlinear with a system of linear equations? So what are some of the things that you may have done different? What are some of the things that you may have done the same? As usual, if you do have any other questions, please leave them in the comments.